Welcome again. In this lecture, we will motivate internal model control. We will explain the consequences of stability. We will compare internal model control and conventional controllers. Internal model control is abbreviated as IMC. The controller has an explicit model of the plant. It is popular in chemical engineering. It is mainly for open loop stable plants. The main benefits are the following. In this framework, if the open loop transfer function is stable and if the controller is stable, the closed loop system can be shown to be stable. This reduces the effort required in searching for controllers. We need to search only among stable controllers. Let us now see the schematic of internal model controller. Let the plant be GP of Z and suppose we model it as G. That is, the plant model is given here with C being noise. Here is the schematic. You can see that it is somewhat similar to what we saw in Smith predictor. Here is the actual plant. Here is the model of the plant. Plant output is Y. This is noise corrupted. Y tilde is the output from the model of the plant and C tilde is fed back. What happens if we know the plant exactly, that is G equals GP, then C tilde simplifies to as follows. So for Y we write as GPU plus C, namely it is here, GPU plus C is Y minus Y tilde, which is nothing but G times U. If G is equal to GP, then it becomes C. What are the benefits of IMC? So this is what we saw in the previous slide. If G equals GP, what we feedback is exactly C. That is, only the noise is fed back. In case of plant model mismatch, suppose GP is not equal to G, then that difference gets added to this C tilde. It is appealing because for stable systems we need feedback for noise rejection and plant model mismatch only. If in addition GQ equals GP inverse, that is GQ equals GP inverse, then GPU, that is the point here, you can see it is equal to what we get from here. Let us assume that R is equal to 0 here, so it is nothing but GQ into GP times C tilde, so that is what we have. So we are comparing the signals here and this is nothing but minus C because GP GQ is identity and you have C, which will cancel the noise resulting in Y is equal to 0. So you get minus C here and there is C here and that will cancel. We already have C tilde equals C as given here. So we have shown that if GP equals G, then we already have C tilde equals C. In addition, if GQ is GP inverse, we get Y is equal to 0. Let us look at the transfer function with auxiliary inputs. We would want to study the stability of such a system. So we are about to study the internal stability. Remember, when we discussed internal stability, we said that for all possible transfer functions in the loop, the system should be stable. You take any 2 points in the closed loop, the transfer function between them should be stable. In order to do that, we introduce 2 auxiliary inputs, U1 and U2, and we derive the expression for the outputs y, u and y tilde, y, u and y tilde, we take this as the outputs. The inputs are external are u1 and u2, and you can see that y is equal to g gq times r, g gq times r. We are of course assuming in this case once again gp equals g, and then the next component is g times u1. You can see this here, g times u1 gets added, and finally u2 is given by this expression. So the transfer function between u2 and y is given here. So we get the first line. Similarly we get the expression for u and the expression for y tilde. I would want you to go through this and verify that you indeed get these. So we have made the assumption gp equals g here. So we will now see that plant and gq stable implies stability of the overall system with gp equals g. So here is the transfer function that we obtained in the previous slide. The system is internally stable if and only if every entry in this matrix is stable. Assume that the open loop plant G or Gp to be stable. Remember Gp equals G. Now G is stable. As a result we see that every entry will be stable only if Gq is stable. As a matter of fact, if Gq is stable then every entry will also be stable. So we need to look amongst stable controllers only, because the internal stability is equivalent to Gq being stable. This makes the controller calculation a lot easier, as I mentioned earlier. I would like to ask this question: can we express the standard controller in IMC form? Why? Because we have already designed the standard controller, we have spent a lot of time and effort. Now we have got a new configuration called IMC. Now it will make sense if I make these two consistent with each other, so that whatever we have done will not be wasted. Here we ask, can we represent the standard controller as IMC? So here is the standard controller GC, here is our plant GP, here is the noise C, reference signal R, plant output Y, and so on. If you ignore what we have below, it is exactly the standard controller configuration. Now I add and subtract G here. What do I mean by that? Supposing I have a signal U, then I have GU here, then minus GU here, then because of this minus we have plus GU coming here because of this. Whereas here this becomes minus GU. Minus GU here plus GU here, they cancel each other. It's as if we didn't have anything. So adding and subtracting produces nothing, no change. It is identical to the standard controller configuration. Now what we will do is, let's look at this dotted line, and you can see that that is nothing but the IMC controller GQ. If you replace this with GQ, this is exactly the IMC form that we saw earlier. Then the expression for GQ is exactly this, GC by 1 plus GGC. So this controller that is used in IMC has an explicit model of the system. For example, this plant G is present as a part of it. So we call GQ as the internal model controller. Can we recover IMC from the standard controller? Recall the equation that we derived in the previous slide. From this it is straightforward to back calculate GC. For example, if GQ is given, we can always calculate GC from this. To conclude, in this method we feed back only noise and plant uncertainties. If the plant is stable, we also need to search only amongst stable controllers to determine GQ. Conversion from and to conventional controllers is easy, as we saw earlier. So this is the strong motivation to consider internal model control law. We will design IMC in the next video. Thanks for joining. Goodbye.